You type one sentence. Behind the screen, billions of calculations race to predict the next word. Unplug the GPU. The AI does not become stupid. It becomes late. The twist? This chip was built to draw game pixels, not understand language. Why did gaming hardware become the engine of AI? Because AI does not need one brilliant calculator. It needs thousands working at once. Soon, even the arithmetic becomes the easy part. First, do not think of a CPU as an outdated GPU. A CPU is more like a small team of master chefs. Each one can quickly follow complicated instructions, make decisions, switch tasks, and react when something unexpected happens. Starting your computer, running the operating system, opening a browser, and controlling program logic all depend on that kind of flexibility. A GPU is more like an enormous kitchen with thousands of simpler workstations. One station may not be as versatile as a master chef, but if the job is to cut 100,000 identical slices of potato at the same time, the room becomes terrifyingly effective. That is the difference in design goals. A CPU tries to minimize the delay of a smaller number of complicated tasks. A GPU gives up some single-thread flexibility to maximize the total amount of similar work completed at once. So the real question is not, which chip is stronger? It is, can the job be divided so that many workers can do it together? For modern AI, the answer is yes. Spectacularly yes. To you, a prompt is language. To a neural network, it eventually becomes numbers. Words, or pieces of words, are converted into vectors. The strengths of the model's internal connections are stored as numbers too. Across many layers, the model repeatedly multiplies groups of numbers, adds them together, normalizes them, filters them, and passes new numbers forward. Arrange those numbers into rows and columns, and you get matrices. Matrix multiplication sounds intimidating, but it has a property that GPUs love. Many cells in the output matrix can be calculated independently. Imagine a gigantic multiplication worksheet. A CPU can fill it with a small number of extremely fast pins. A GPU can place thousands of pins over different cells at once. That does not mean every AI operation is perfectly parallel. Layers still depend on earlier layers, and some steps must wait for others. But inside each layer, there can be huge numbers of multiplications and additions ready to happen together. And neural networks perform this kind of work again and again and again. Language creates a complication. Words have an order. Older recurrent neural networks behaved more like a relay race. One step handed its result to the next step, which then continued. You could not let every runner start at the same time, because the later runners were waiting for the baton. The transformer changed that arrangement. Its attention mechanism allows many positions in an input to compare their relationships during the same stage. Underneath, the model is still doing enormous amounts of matrix math, but more of that work can spread out in parallel. This does not make a transformer completely free of sequence. It still has many layers. And when it generates text, it still produces one token after another. But during training, examples can be processed in batches. And while reading a prompt, many positions can be processed together. Instead of feeding the GPU a narrow line of jobs that mostly wait, the model can give it a busy factory floor. The meeting between modern AI and the GPU was not an accidental brand story. The structure of the algorithm happened to fit the structure of the hardware. Training a neural network is not the same as copying knowledge files into a chip. The model looks at a batch of examples and makes predictions. The system measures the difference between those predictions and the targets. It sends an error signal backward and adjusts a huge collection of parameters. Then it loads another batch and repeats the process. Forward pass, error, backpropagation, update, once, again, and again. The GPU does not understand cats, poems, or computer code. Its advantage is that it can compress a vast amount of repeated mathematics into every training step. In 2012, AlexNet trained on two GTX 580 graphics cards for roughly 5 to 6 days. The paper itself said that the size of the network was limited mainly by available GPU memory and by how long the researchers were willing to wait. That moment matters not because those old graphics cards are still impressive. It matters because they demonstrated that parallel hardware built for images could carry deep learning across the gap between possible in theory and useful in practice. Today, machine learning frameworks can move models and tensors onto GPUs or other accelerators. Very large training jobs divide work across many devices. But the core idea remains the same: make enormous amounts of similar math happen at the same time. Training is heavy, but when you talk to a chatbot, the model usually is not retraining itself. It is performing inference. Large language model inference has two very different moods. First, the model reads your prompt. Many positions in that prompt can be processed together, so the GPU has plenty of parallel work. Then the model begins to generate the answer. It produces one token, places that token back into the context, and only then can it calculate the next token. A sequential chain appears that cannot be completely removed. At this point, the bottleneck is often not just, can the chip calculate fast enough? It is, can the data arrive fast enough? The model's weights have to be read from GPU memory. As the context grows, the cache holding intermediate attention information also grows. Even thousands of calculation units can sit idle if the data they need does not reach them. That is why the competition in AI hardware is not only about the number of cores. Memory capacity, memory bandwidth, connections between devices, and software that batches requests efficiently can matter just as much. This is the second secret from the beginning. In a large language model, moving the numbers can be harder than calculating them. Now we can correct one word in the title. AI does not logically require a GPU. Small models can run on CPUs. Phones contain dedicated neural processing hardware. Data centers can use TPUs and other custom accelerators. GPUs won a crucial position because they balance several things unusually well. They are general enough to run many different models. They are parallel enough to accelerate tensor operations. And they have a mature software ecosystem, so researchers do not have to control every transistor from scratch. The CPU never disappeared. It still runs the operating system, controls program flow, prepares data, schedules work, and handles large amounts of sequential logic. A real AI system is more like a relay. The CPU organizes the job, hands parallel sections to the GPU, and receives the results. If a task is too small, contains too many unpredictable branches, or costs more to move onto the GPU than it saves in calculation, the CPU may be the better tool. A GPU is not a universal hammer. It is simply an unusually good match for the most expensive part of neural network work. The next time an AI writes an answer in a few seconds, you will see words. The machine sees vectors, matrices, weights, and caches. The CPU organizes the flow. The GPU allows thousands of calculations to happen together. Memory keeps delivering numbers to wherever they are needed. The chip does not understand your question. It performs the mathematics of the neural network quickly enough for a result that resembles understanding to arrive on time. That is also why GPUs have become so important, so expensive, and powerful enough to influence which organizations can train larger models. The limits of modern AI are not set only by algorithms and data. They are also set by how much a chip can calculate, how much memory can hold, and how quickly numbers can move. A prompt appears to have no weight, but before it becomes an answer, it must pass through a physical machine. And that is the strange story of modern AI. A chip originally built to draw imaginary worlds now helps calculate language, images, and an increasing number of decisions in the real one.